Digital Twin session. Thanks everybody for attending, for being here, having this virtual session going, and hope you're all well and safe at home, hopefully, during this third wave we're having in South Africa for COVID. So today we've got Edward Carmen from the UK to present to us really how Ansys Digital Twin and how we can use our digital twin concept to ideally help our customers. There's some cases from the UK that we're sharing, and we're trying to demonstrate how that can hopefully be used within the South African industry as well. So Edward is one of our senior applications engineer. He's based in the UK in Sheffield, and he actually used to work for Qfunsoft as well. So he's relocated, but still, as you can see, very good connections. For those of you that don't know Qfunsoft, we are the sole suppliers of Ansys simulation software in Southern Africa. We do sell Ansys simulation software as well as the Rocky DEM, which is more the discrete elements software. And I'm now happy to hand over to Edward, and then we'll take questions afterwards. So please mute yourself. If there's any questions you have to ask during the session, raise your hand. Alternatively, we'll give some time afterwards for questions. So Edward, I'll hand over to you now. Thanks a lot.
Thank you very much, Laura. And once again, it's very nice to be working with Qfunsoft again. And on behalf of Ansys, I'd like to welcome everyone. So today, I'm going to talk about how we can use Ansys simulation within the digital twin to expand the digital twin. I think it's always important when we do these conversations, we start off establishing some definitions for what the digital twin is. Then we'll look at some of the sort of key parts that make up the digital twin, what we need to build one of these, how we can add our physics simulations into the digital twin, enable that data that we've already got, and how Ansys Twin Builder enables us to cross that bridge. And finally, we'll look at some of how this knowledge can be applied onto industrial use cases with some customer examples. So digital twin is an emerging concept, and it can be quite different depending who you talk to, what the definition, what they see as a digital twin. It's becoming more formalized, and the Digital Twin Consortium, of which we're a founding member, has come up with this definition that a digital twin is a virtual representation of a real-world entity, a thing or a process actually. And importantly, we're synchronizing data with that entity at a given frequency and fidelity. So we have something in the real world, we have its virtual representation, and we're sharing data between them. And this is allowing us to do things like tracking the past behavior of the asset, so giving us a central repository to sort of store the history of the asset and connect it to that asset. We've also getting deeper insights into what's happening to this asset in the present. How is it running at the moment? And then finally, we're also looking importantly at predicting what it's going to do in the future, and even more interesting, influencing how it will behave in the future. And we're seeing significant benefits from this. For example, increasing revenues. Companies look at ways they can actually change their business model. If, for example, you look at jet engine suppliers these days, very seldom are they supplying just the jet engine, just the new equipment. They're actually selling the service. So you won't buy a jet engine, you will buy flight hours, and they will guarantee you'll have so many flight hours per year with a certain amount of uptime. And that changing revenue model. You're looking at ways of reducing costs. So if you look at the sort of costs of maintaining an asset, how high they might be compared to the productive revenues. So if you can save on those costs, you can again increase revenues. And companies are also looking at it as a way of gaining a competitive edge. If we look at how many assets we expect to be under some kind of condition monitoring by the middle of this decade, it's a vast number. And if we can leverage that data and use it to improve the assets or improve our offerings, we will gain this edge. We see digital twins across many industries. We've mentioned aerospace with maintenance on jet engines. The automotive industry has interest both from improving their production processes and also looking at things like fleet maintenance or vehicle maintenance. We're looking at manufacturing, where we might be looking at, again, optimizing of production, speeding up commissioning, improving safety even, buildings and infrastructure. We're looking at ways we can make buildings more energy efficient. Using our digital twins with that data allows us to start doing that. And things like oil and gas and resources production, where, again, the digital twin improves the operation, but also importantly, improves the maintenance, reducing downtime, keeping these productive assets producing revenue. Though the business case for a digital twin, sort of falls into two categories. This is where it's most successful. The first category is where we have single assets, but these are very expensive assets. So we have very expensive equipment. And an example is Verbund Hydro, which is a supplier of hydroelectric turbines into sort of Germany and Europe. You can see one of these turbines, a very large asset, can cost millions of euros. And it's very important with these large assets to optimize their operation, to improve the return on investment, but also to ensure that you're monitoring their structural damage and specific wear under different operating conditions, because you want to get the most from these assets. We can also look at cases where the asset itself might be relatively inexpensive, but it's part of a much larger and expensive process. So the asset might be cheap, but if it stops working, you are slowing down or stopping a valuable process. And examples of this might be uplift pumps that are used within the oil and gas industry. So pumping product from the sea floor, or for example, pumping something out of a mine. If this asset fails in an unplanned manner, you are shutting down your oil well, you're shutting down your plant, and you are not generating revenue while that is happening. So if you can anticipate or prevent those unplanned shutdowns, there's significant savings to be made. So the key elements that build up a digital twin, we need to have a number of things in place. And I like to sort of build this from the bottom. It's kind of like building a pyramid. So at the fundamental level, we need our assets. We need something in the real world. We need a process which we're monitoring. We need a physical thing. And related to that asset, we also need the infrastructure around it. So we need things like the sensors. We need the hardware to take the data from the sensors, transmit it somewhere. And once we have that infrastructure in place, above that, we then need somewhere to actually hold and manage this data. We're generating huge amounts of data in some of these applications. So we need a platform to hold it, to store it, to manage it. And once we have this huge amount of data, we need to make sense from it. If you think about it, if you have 100 pumps, each one with 10 to 100 sensors measuring values every 100 milliseconds, you're generating huge amounts of data, which a single human probably can't really get the best out of. So this is why we have the third level, which is the data-based analytics. Approaches like machine learning, deep learning, even just curve fitting and visualization, allowing us to take this huge amount of data and turn it into useful information. And these three levels comprise what one might call the traditional digital twin. And we have open ecosystems in this space and also key partners. So people like SAP or PTC or Microsoft are working well in this space. What Ansys is offering is something above the traditional twin. It's saying, take this vast knowledge of simulation, physics-based simulation, understanding of physics, and use it to augment the traditional twin approach. Address some of the deficiencies in the traditional twin approach, and don't replace it, but add something else, some extra value on top of it. And we can now look at the reasons why we might want physics-based simulations within a digital twin. And it really just comes down to not having enough data. If you're doing pure data analytics, you can only gain insights from the data you have. If you don't have the data, you can't do anything, do any useful analytics with it. And simulation looks at filling holes in the data in a number of ways. So the first one of these is we create what we call virtual sensors for measuring missing data or for measuring data which is actually either expensive or impractical or almost impossible to measure in the real world. If you think of something like we're doing some work with people who are working on fusion reactors, they want to know the temperature inside a fusion reactor, but considering the temperatures there mirror the surface of the sun, most thermocouples and traditional methods don't survive. But we can use our physics-based simulations, our understanding of the heat transfer, of the reactions inside these vessels. We can then get a good prediction of the temperature based on the things we can measure, such as the power input, the rate of neutrons going into the system and so on, or for something like an electric motor. We could stick a thermocouple inside the rotor on an electric motor, but perhaps we're trying to retrofit, so it's difficult to do that, or it actually just adds too much to the cost of the motor to make it practical. But we can use a simulation to take things like the current and the speed of the motor, which are easy to measure and which we are already measuring, and again, using our understanding of electromagnetics and heat transfer, predict the temperature or the things that we can't measure. Simulation can also be used to perform what-if scenarios. This is a it should be a familiar approach for anyone who's done simulation. You're trying to test out what would happen under different situations. If you're using pure data analytics, if I wanted to know what would happen if I were to switch off a certain set of valves in order to reroute flow around a pump to do some maintenance on that pump, if I wanted to know how that would influence the rest of the system, if I'm using pure data analytics, I will only get that knowledge if I've already done it before in the past. But if this is the first time I'm doing this, I have no way to go. But I can use a simulation to fill in that data. So predict what would happen under different configurations using my physics simulations. Simulation can also give us accurate and deterministic predictions based on our physical principles. So what do we mean by this? Again, if we're doing data analytics, we're taking data, the outputs, and we're looking at it to find patterns. But we don't know if those patterns are generally applicable. For example, we could be running a generator in the middle of Siberia under sub-zero Arctic temperatures, and we've gathered a lot of data for how that generator is operating. But we can't necessarily be sure that we can take that data and apply it to a similar generator running in the middle of the Sahara. We don't know that if those patterns will transfer. Whereas if we have a simulation model, which we've built from the ground up based on our physical understanding of this motor, we can apply that in different locations because we understand what parts of it we need to tweak or what settings we need to change to get good predictions in different areas. And finally, again, we can use simulation to explore things like causality or failure mode predictions. If we're doing traditional data analytics, we might see a deviation from baseline behavior, but we can only connect that to a specific failure mode if we've previously seen that failure mode and tied that sort of data to it. Whereas a simulation, we can start simulating these failure modes to get an understanding of what they might look like. So when we start seeing them in the field, we can immediately connect them, say this abnormal behavior, this vibration is specifically caused because we have an imbalance in the turbine blade, giving us much more nuanced and much more effective maintenance interventions. So we're seeing the value of Ansys-based, physics-based digital twins are used in industrial applications in sort of three main areas we're seeing it. So the first is things like troubleshooting problems, configuring systems, or commissioning systems virtually. So testing configurations out, testing different solutions out before you implement them in the real world. We're also looking at the big one, which is predictive and prescriptive maintenance, using our simulation models to predict things like degradation or wear, using a stress model to predict the fatigue damage, which predicts the remaining useful life on our hydraulic turbine operating under its specific operating conditions, which may be different from the same turbine operating under a different load cycle or in a different region. And finally, we're also looking at digital twins as a way of optimizing production or improving the yield of our products. So things like yield as a service, which is the sort of business model for a lot of jet engine suppliers, or optimizing production runs, as I'll show you with the refinery example at the end of this presentation. So before we look at TwinBuild itself, just a quick touch into one such example is this was work we did with a consumer packaged good company, and they're looking at virtual commissioning of their factory equipment. So the problem is that they have a production line that they can change over from, for example, producing hand soap to producing shampoo. And they need very tight control on the quantity and flow of the raw materials. So when you change from soap to shampoo, your mixes change, and they change quite often to different lines. And the problem is every time they do that, they have a bit of a trial and error exercise. They need to feed in the raw materials, change the valves, and wait for it to come through the process before they can monitor the quality of the finished product. They then go back, change some other things, have it keep running some more. And so this commissioning can take a number of hours. What they found, though, is by using simulations, measuring the flow from the different bins, the different valve states, the pump states, they could start getting a real-time prediction of what the product quality would be before it went all the way through the process. So they could start making interventions and tuning things before they would previously have been able to, which has allowed them to look at reducing the changeover time from hours to minutes, because they can do this virtual testing much faster than the real world testing. So if we want to build one of these things, this physics model, we're using Ansys Twin Builder, which is a system simulation tool at its heart, able to take multiple technologies, different models, leverage our existing 3D models, share models, and ultimately deploy them as runtime applications. And the architecture we do this, we can see here. So on the left, we have Twin Builder. This is our system simulation tool. We could use this to design a system. We can simulate it, test it under different environments, and we build this system with component representations from different sources. So we might have libraries of simplified components, represent a pipe with its pressure drop equation, for example, or a resistor with a simple voltage is equal to current times resistance equation. But we can also take advantage of the existing complex 3D physics models we already have. We've often used these as part of component design. And through reduced order modeling tools, we can bring in this very computationally expensive but very accurate models into our digital twins, where we can get similar accuracy, but to run them a lot faster. And once we've built up the system model, we need to export it into a form that is scalable and lightweight for running on digital twin deployments. So we export what we call a runtime, which is the model wrapped with an SDK to manage the data transfers. And we can deploy this onto scaled environments, so onto an IoT platform, or create a simple Python app that could run in the cloud, deploy it from Windows, deploy it to Linux. All of these different things are enabled and made much easier using Twin Builder. So to close off, I'm going to show you a simple industrial example where we worked with a petrochemical refinery on a challenge to optimize their blend processes. So the challenge they face is that they have quite advanced blend optimization tools. And they use these, for example, to say, if I need to produce a certain grade of gasoline, which product should I be using from which tanks? The different tanks can have different qualities. They can have different costs, different supply constraints. How do you combine all of these things together to achieve an optimal blend, produce it in the time required, at the rate required, subject to constraints such as the plant layout and certain assumptions of flow delivery rates? And this is a very advanced tool, but the problem is that in operation, certain things like very complex fluid mixtures, different viscosities, or sort of slow degradation or clogging of lines can lead to situations where the flow limits that the blend tool assumes and provides to the production team aren't actually achievable in the real world. And this means that either the blend can't be produced at the rate that's required, or you get a suboptimal blend that either needs to be sold at a lower grade or needs to be sent back for reprocessing. So the goal of our twin model was to say, well, given a certain blend and the layout that's been chosen by the optimizer, can we calculate the actual achievable flow rates before we switch this on and start putting it through the plant? And then once we've done that calculation, can we check that the blend is actually feasible? And if it's not feasible, let's feed this data back to the optimizer to tell it to recalculate the blend with the updated information. The overall solution architecture looks something like this. We have our system information, so our PNIDs, our data sheets, our imagery. We use this to build a system model. That system model is then deployed as a runtime to live on an IoT platform, and that's then sharing data with the physical asset, which is the blend tool in this case. And the physical problem we're trying to solve should be one that's quite familiar with anyone who's used pumps or piping applications. We have a certain pump curve, which is available to the blend tool, and we have a certain maximum flow rate. The blend tool also has certain assumptions about how the system will perform. So it's not just guessing numbers, it has some idea of how the system should perform, and it assumes a certain flow rate can be achieved. However, what's happening in real operation is because of this complex mixing of different lines, different branches, more complex blends, and also the degradation on some lines, the actual system curve, the actual performance curve is different to what's assumed by the optimizer. And so we're getting a true calculated flow rate. So the actual flow rate of what we're trying to calculate with the simulation. And the situation we're trying to avoid is where the optimizer has assumed one flow rate, but it can't actually achieve that flow rate in the real world. And so we're trying to predict this and anticipate it and then re-optimize as we go. So we build our system model. We start off with a sort of generic model made up of different components, different branches, and we can swap out different components for the different lines, the different mixes, the different manifolds, and so on. So we can take a modular approach, which allows us to reuse a lot of work and a lot of data that we've already got. For example, for specific models, specific lines, we're using libraries of standardized components, so we don't have to write everything from scratch every time. And we're integrating the actual plant data. So for example, the flow coefficients for valves or specific valve curves can be implemented in these components. We can also do things, for example, where we are lacking complete data. So we don't have complete data for the length of all the pipes, but we can do things, for example, we can measure it on Google Maps or something, estimate the lengths, which then gives us a starting point that once this twin is running with the measured data for flow and back pressure that we're getting from the plant, we can start calibrating our twin online. So tune some of our parameters, fill in the gaps for where we don't necessarily have the data. So it's a true twin. Our twin is telling things to the real world, but the real world is also telling information to our twin. And then finally, we can implement things like pump data sheets, valve curves, and the like. Once we've built these models, we then generate the platform-specific runtimes. So take the models, export them in a form that will run on Azure Digital Twin in its operating system environment. And these are connected to the Twin through an API, which was implemented by Microsoft. And this represents all the possible ways this flow could go through the plant. And then based on what the optimizer decides is the best routing, we select a subset of scenarios. We simulate them with our deployed models, and we get a prediction of what the achievable maximum flow rates are for each branch. And from that, we can then go back to the optimizer and either tell it, hey, you're good, you've assumed something that you can achieve, or you know what, you're assuming some limits which actually aren't achievable, guess again, or calculate again, but here are the new limits for your calculation. And this allows us to achieve better blends. So in summary, the challenge they were facing was that the efficient blending needs to account for different gasoline blades, different mixes. The traditional tools can't necessarily account for that. And so by using simulation, we can account for specifics of the specific blend, confirm the limits, and as a result, reduce the amount of rework or reduce the amount of degradation for these blends. So in conclusion, we've talked about what we see as a digital twin. Real asset, its virtual counterpart, and the data sharing between them. We've looked at the key elements of a digital twin. The asset and the sensors, somewhere to put the data, something to make sense of the data, and simulation to add even more insight onto the data. We've shown how simulation fills in these holes in the data lake. We've shown how Twin Builder can be used to build these physics simulations. And finally, we've also shown how this could be applied to specific use cases, such as this gasoline blending application. So with that, I'd like to thank you very much for joining me.
Thanks a lot, Edward. I must say that was very informative, and thanks for sharing the use cases of the industry as well. I think that really helps to bring the whole theory into the real world and how it can be applied. So thank you very much. Now it's open for questions. So I think there was a pop-up asking about what's a ROM. So that's a reduced order model. Is there any other questions from anybody attending? Ja, Peter Venter, you can ask your question. You unmute yourself, thanks.
Edward, in your opinion, what are the advantages that the Ansys tools provide over competitors? Why I'm asking is that it also seems as if everybody's jumping on the bandwagon, and there's a lot of promises out there. But in real world advantages or scenarios, what would you say are the benefits of using the Ansys tool set over somebody else's? Thanks.
Okay, yeah, that's a good question. So I think there's a couple of key aspects. So the first one is, I mean, we heard about reduced order modeling. So one of the key things with our tool set is reduced order modeling, which is a way of taking very complex 3D simulation models and taking that data and compressing it down into a form that we can run in these digital twins. So essentially, if you can't get data from a simpler model, you need those 3D models, but they're too heavy for digital twins. So we compress them down and run them in that digital twin. We have the tools associated with that. Also related to those reduced order modeling tools is the workflow around them. So not just, I mean, other companies also have tools for building reduced order models, but our workflow to make it easier to do it for a user is more advanced. Other aspects, Twin Builder as a system simulation platform is quite open in the sources of data we can take. So we can bring in models from that have been generated, say, in Simulink, or have been generated in other third-party tools, bring them into Twin Builder, incorporate them into our system simulations. And then the other aspect which we are seeing with our customers, where they are quite sort of keen on our offering, is in this aspect of taking this model and creating these deployable runtimes. So we have quite a nice simple workflow to say, well, here's my system model, export it as a runtime, and then build a very simple application around it. So mostly user interface based, so you don't need to sort of be a guru on opening ports and all sorts of other things to connect it. It's almost a plug and play solution to go from twin model to something that can run in an IoT environment. I think those are some of the key aspects of it.
Thank you very much.
Okay, thanks, Edward. There's another 2 questions in the chat, which I can see now. Let me just make sure there was nothing earlier. Yes, so are there biomechanics or biomedical use cases that we can share?
So I don't have any specific shareable ones, although we have used it in some of those applications. So we've done some work on things like insulin pumps. And we also had quite an interesting application where we applied our reduced order modeling tools to actually looking at sort of inhaled drug delivery through someone's lungs. So how you could take essentially a generic lung model and with some tuning of parameters, make something that's more patient specific in order to look at, say, drug delivery into their lungs. So that was another interesting example.
Okay, and we'll try and share that afterwards with you. So then the next one is from Benny. Benny, you're welcome to ask your question. Otherwise, would it be possible to see a demonstration of the Twin Builder application to a use case at some stage? So I guess that will be specific to Benny's industry.
Yeah, I mean, I think, yeah, we can have specific conversations in a different forum. I mean, we could also, I'm sure Laura would be happy, we could organize a more specific Twin Builder webinar or something. I mean, this was really about the high level of what is the digital twin. We could also have a different thing for a different audience to go into, well, let's drive Twin Builder and actually show you how I would build a runtime application, for example. So it's certainly possible to demonstrate it. I think maybe today is not necessarily the forum for that.
Okay, then I think it's Peter van Schalkwyk. Do you want to ask your question? Is it Peter? Otherwise, does Ansys as a company provide training to users upon purchasing of software? And does Ansys provide a once-off purchase option or a yearly license package? So I think it's Peter van Schalkwyk. Yes, we provide training on purchase of software, and we provide monthly, annual, or paid up options with also elastic license options. So we will take that conversation up with you as well. Okay. Is there any other questions from anybody that I might be missing? Yes, and just to confirm, the recording will be available to everybody afterwards. I'll send it. If there's any other questions, you're welcome to unmute yourself and just